Electrical Measurements and Instrumentation, Lecture 4. In this lecture, we will discuss analog ammeters, voltmeters, and ohmmeters. Analog ammeters and voltmeters are classic together and there are no fundamental difference in their operating principles. The action of the ammeters and voltmeters depends upon a deflecting torque produced by an electrical current, except in electrostatic type of instruments. So the action is same in both ammeters and voltmeters. And in ammeters, this torque is produced by a current to be measured or by a definite fraction of it. In a voltmeter, this torque is produced by a current which is proportional to the voltage to be measured. So in both the cases, this deflecting torque is proportional to current. That's why current is the actuating quantity in both ammeters and voltmeters. The essential requirements of any measuring instruments are: whenever you introduce an instrument into a circuit where measurements are to be made, it does not alter the circuit. That is the first point. When we introduce a measuring instrument into a circuit, it will not affect the circuit. The second point is, the power consumed by them for their operation is small. The power consumed by the instrument must be small. Coming to the ammeter, if you see here, ammeters are connected in series in the circuit whose current is to be measured. There is a battery and a lamp here. Some current is flowing through like this. So ammeter is connected in series in the circuit where we measured the current. The power loss in an ammeter. In this ammeter we have resistance. Because of the resistance, some voltage drop is there. Because of that voltage drop, some power loss is also there. That is I square into R. The current flowing through the ammeter with the resistance in the ammeter, where I is the current to be measured and R is the resistance of ammeter. Therefore, ammeter should have low electrical resistance. Otherwise, if the resistance is more, the power losses are more. As we discussed in the last slide, the power loss must be small in all measuring instruments. Therefore, an ammeter should have a low electrical resistance so that they cause a small voltage drop and consequently absorb small power. Coming to the effect of ammeter on circuit. And this is a circuit, some voltage is applied across a load R, and this is your ammeter resistance smaller. Connect ammeter in series. Are we measuring the correct current? The current in the circuit without ammeter. Without ammeter, the resistance is 0 here. Total current I is equals to V by R from Ohm's law. Any ammeter have some resistance. Let us assume that resistance is R here. The current in the presence of ammeter is I is equal to these two resistances are in series, R plus R. So total current I flowing through this circuit is V by R plus R. Current without the ammeter would be I is equals to V by R. To minimize errors, ammeter resistance R must be very small. In ideal ammeters, we have zero resistance. Let's take an example. An ammeter of resistance 10 milliohms is used to measure the current through 10 ohms resistor in series with a 3 volts battery that has an internal resistance of 0.5 ohms. What is the relative error or percentage error caused by the ammeter? So ammeter internal resistance is 10 milliohm. We are measuring the current flowing through this 10 ohm. It is in series with 3 volts of battery with an internal resistance of 0.5 ohms. Actual current without ammeter. Let's see, without ammeter, the actual current is these two are in series resistances. So 10 plus 0.5, 10.5, and the voltage is 3. So the total current I is equals to V by R plus R. So 3 by 10 plus 0.5, it is 10.5. Therefore, I is equals to 0.2857 amperes. It is nothing but 285.7 milliamperes. The current flowing through this 10 ohms resistor without ammeter. So when we connected this 10 milliohms ammeter, so this is the 10 milliohm ammeter. We are connected one ammeter here. That equivalent resistance is 10 milliohm. Now, the total current flowing through the circuit is I is equals to V by R plus small r plus R here. So where here 3 by 10 plus 0.5 plus 10 into 10 to the power of minus 3, that is 0.01. So the total current is equals to 285.4 milliamperes. Let's say the percentage error is 0.2857. That is the previous without, this is without ammeter minus with ammeter by without ammeter into 100. So the percentage of error is 0.1%. When this ammeter resistance is low, the power losses are low, the error may be 0.1%. Coming to the voltmeters. Let's see the battery here, the resistance, the load. We are connected one voltmeter here. Voltmeters are connected in parallel with the circuit whose current is to be measured. So wherever you require voltage in a circuit, we are connected the voltmeter in parallel. So the power loss in an voltmeter is V square by R, where V is the voltage to be measured and RV is the resistance of voltmeter. Therefore, voltmeter should have a high electrical resistance in order that the current drawn by them is small and consequently absorbs small power. In ammeters, the resistance in the ammeter should be small, and in voltmeters, the resistance must be high. When the resistance is high, the power is inversely proportional to the resistance here in voltmeter case. So obviously, the power loss is less when the resistance in the voltmeter is high. That is a major difference here. In ammeters, the resistance of the ammeter must be small. In voltmeters, the resistance of the voltmeter must be high. If the meter's moving system has only a small resistance, additional resistance will be included in series with the moving coil. That resistance is called as swamping resistance. Let's see the effect of voltmeter on circuit. And this is our previous circuit. So 0.5 internal resistance of this battery and 10 ohms load. Now we are calculating the voltage across these 10 ohms. Then we connected one voltmeter here. The voltmeter resistance is R. Yeah, we are measuring the voltage drop or potential difference between A and B terminals. We know that connected voltmeter in parallel. If you want to measure the correct voltage without voltmeter, measuring the correct voltage. So voltmeter have some resistance. That resistance is RV here. The current flowing through this voltmeter is IV. Extra current changes voltage drop across R and this VAB. To minimize error, voltage resistance R must be very large. Ideal voltmeters would have infinite resistance. Let's see an example in the case of voltmeter. A galvanometer of resistance 60 ohms is used to measure the voltage drop across a 10 kilo ohms resistor in series with an ideal 6 volts battery and a 5 kilo resistor. What is the relative error caused by the non-zero resistance of the galvanometer? Let's see here. It is our 10 kilovolts. This is our internal resistance of the battery, and we are going to measure the voltage across this 10 kilovolts. And the internal resistance of the voltmeter is 60 ohms. So actual voltage drop without instrument. Now I am not connecting any instrument here. I am simply checking what is the voltage drop in this resistance. So for that, these two are in series. So 10 kilo ohms plus 5 kilo ohms. So 15 kilo ohms. So 15 into 10 to the power of 3 ohms. So the total current is equals to 6 pi 15 into 10 to the power of 3, which is 0.5 milliamperes. So this 0.5 milliamperes into this resistance will get the voltage drop here. So that is 4 volts. So without instrument, the voltage drop across A and B is 4 volts. Let's see with voltmeter. We are connected our voltmeter here having 60 ohms internal resistance. These two are in parallel. We get almost 59.6 ohms resistance here. So that is in series with 5 kilo ohms. So total equivalent resistance is 5059.6 ohms. And the current flowing through here it is 6 by 5059.6. We'll get 1.186 into 10 to the power of minus 3 amperes, which is approximately 1.19 milliamperes. The total current flowing from the battery is 1.19 milliamperes. And VAB is equals to, if you apply KVL here, minus 6 plus 1.19 milliamperes into 5 kilo ohms plus VAB. Right. Plus VAB is equals to 6 minus IR2. Here I is equals to 1.19 milliamperes and R2 is equal to 5 kilo ohms. We'll get VAB is equals to 0.07 volts from KVL in this way. Once it is 0.07 volts, obviously the voltage across this voltmeter is also 0.07 volts. The relative error is previously without voltmeter, which is 4 volts, with 60 ohms internal resistance voltmeter having the voltage drop 0.07. The percentage of error is 98%, which is very high. Will you pay for this voltmeter? We need a better instrument. So for that, I'm changing my resistance here 60 ohms to 100 kilo ohms. Now I'm changing my voltmeter internal resistance from 60 ohms to 100 kilo ohms, almost 1 lakh ohm. And we calculated this voltage. Without voltmeter, we have 4 volts. And with an instrument, now it is 100 kilo ohms. And these two are parallel, and which is in series with 5 kilo ohms. Finally, the total equivalent resistance is 14,090 ohms. And the total voltage is 6 by 14,090. We will get 4.26 into 10 to the power of minus 4 amperes. Whenever you're finding the voltage drop VAB, apply again KVL here, minus 6 plus 0.426 into 10 to the power of minus 3 into 5 10 to the power of 3 plus VAB equal to 0. Then VAB is equals to 3.87 volts. From KVL, we'll get VAB is equals to 3.87 volts. This voltage is appear across this voltmeter. Without voltmeter, we'll get 4 volts. With voltmeter of 100 kilo ohms resistance, we'll get 3.87. Finally, the percentage error is 3.25, which is better than previous one. So not great, but much better. So whenever the internal resistance of the voltmeter is more, the percentage of error is very, very less. That's why in ideal voltmeters, we are considering the resistance in the voltmeter is infinite. Let's say the design of a voltmeter. So voltmeter must have a very large resistance. Voltmeter can be made from galvanometer in series with a large resistance. So like this. And everything inside the blue box is the voltmeter. It's completely called voltmeter. Let's see the errors in ammeters and voltmeters. There are majorly 2 errors in voltmeters and ammeters. There are friction and temperature errors are perhaps the most important. To reduce the effect of friction torque and consequently the error produced by it, the weight of the moving system must be made as small as possible compared with the operating force. If you want to reduce the frictional torques, we need to make the weight of the moving system as small as possible. That is, the ratio of torque to weight must be large. The torque is high, the weight must be very, very low. If you maintaining this, will reduce frictional errors. So in high quality instruments, the ratio of deflecting torque at full scale to the weight of moving system is rarely much less than 0.01 Newton meter per kg. The vertical spindle is generally preferred to an horizontal one from the point of view of a small friction torque. The second one is temperature error. The most serious error is produced by the heat generated in the instrument or changes in room temperature. Is that due to the changes in the resistance of the working coil? Such a change of resistance is very little in the ammeter, but in voltmeters, in which the working current is proportional to the applied voltage, it is essential that the resistance of the instrument remains as nearly constant as possible. Thus, the power loss in the instrument should be small, and resistance coils which are likely to produce appreciably heating should be mounted. If possible, in such a position that they are well ventilated. In order to eliminate the temperature errors, the working wire is wound with the copper wire, and is of comparatively low resistance. Coming to the ohmmeters. So ohmmeters are used for measurement of resistance. They incorporate a source of EMF and a current measuring device. Basically, ohmmeters measures resistance of an isolated resistance only, not in the working circuit. Thank you.